Well, I don't think I'm going to run long. I was running long in my practice talk, and I started cutting slides out on the plane, and I might have gone a little crazy. Anyways, my name is Mike Hawkshaw. I'm a PhD student at the University of British Columbia, and I'm working on a case study involving Pacific salmon management on a Pacific salmon fishery operating on the Skeena River in northern British Columbia. My project as a whole is a pretty big modeling effort, building components that can go together into a management strategy evaluation. This is, I should probably mention at this point, this is a project under the auspices of the Canadian Fisheries Research Network, and it's in collaboration with both the commercial fishing industry and some of the government scientists in the region. Yeah, so I'm going to talk about the linear programming part of the work that I've done. So, how are we doing here?
It's down to one.
I only got the one slide, so. There we go. All right. So I thought I'd show a map. Again, the Skeena River is kind of on the left side of Canada, up near the border with Alaska. I think the only people in the room who know where it is, and everybody else isn't really going to be helped by that, but I guess it's traditional, right? So in my talk, I'm going to go over 4 main areas. I'll outline a management problem. I'll hopefully explain some of the kind of ongoing proposed solutions, and I'll show how the linear programming that I'm doing, I think, is probably the best solution. Yeah, and then I'll talk about some of my results and next steps. All right, so Pacific salmon, just to get everybody on board, I think they have a fascinating and varied life history. All Pacific salmon species reproduce and have a juvenile growth period in fresh water. Then they migrate to the ocean, where they spend a variety of years, depending on the species and stock, dispersed and feeding. Then they concentrate and do a migration back to their natal streams, where they spawn and die. One of the neat things for me about Pacific salmon is how that migration timing is very precise, and how quickly they move once they start that migration. So on the Skeena River, there are commercial fisheries. There's a troll, seine, and gillnet fishery, though the bulk of the fish harvest is taken by a gillnet fishery right at the mouth of the river. There are a variety of different fishing areas. However, again, most of that fishing happens in one fishing area at the mouth of the river. In addition to the commercial fisheries, there are Aboriginal food, social, and ceremonial fisheries, and there's a large and growing recreational fishing component. I guess as a personal note, when you're trying to model a complex of fisheries, when 2 of the components are not especially well monitored or well controlled, it is a little bit frustrating, but I'm sure everybody here has had to deal with something like that. Salmon management strategies in general. So historically, salmon management were usually managed to a fixed escapement target, which means that the goal of the fishery manager was to allow a precise number of fish to escape the fishery. And that target escapement would allow them to maximize the return of the spawning fish. And these are just a couple of graphs showing the target catch at different escapement levels, or the target harvest rate at different escapement levels. Historically, management on the Skeena has actually been quite successful at managing the aggregate sockeye salmon stock to that target. So that's like 95%. The historic catch is 95% of what you would get with perfect implementation of an MSY strategy on the aggregate sockeye stock. There's been some changes though, and there's been an emphasis on mixed stock fisheries management. So instead of managing to the aggregate stock, you're now supposed to manage the different sub-stocks on the watershed. This has led to some, I think, pretty understandable management challenges. Whereas before you were managing an aggregate stock, now on the Skeena, just as an example, there are 32 identified sockeye stocks, 12 Chinook, 4 coho, 4 chum, and 5 pink salmon stocks. And the harvest impacts are supposed to be managed for all of those stocks. And that's an astonishing increase in complexity. And currently, people are working on ways to address this, but currently it's mostly being managed in an ad hoc way with temporal closures. They have some stocks that they don't want to harvest at the end of the fishing run and some stocks that they don't want to harvest at the beginning of the fishing run. They're closing the fishing period to avoid targeting weak or recreationally important stocks. So how can we move beyond kind of ad hoc temporal closures? There's a couple of ideas. The main one is to use a stationary functional relationship between stock size and your harvest in order to meet some multi-stock objective. Now, this is an example of a figure from a coho salmon analysis where they were examining the aggregate escapement required in order to meet those stock-specific escapement targets. So you can see that you want to be on the zero line there. So you can see that in order to meet in order to meet your first stock-specific target, you want an aggregate escapement of 20,000 or higher fish. In order to meet your second stock-specific target, you want to have an aggregate escapement of 40,000 or more. And that's, there's a way to manage your stock-specific targets with an aggregate escapement target. There's a key problem with this is that the kind of your expected run size for a large run on this system is between kind of 40 and 60,000 fish. So in order to meet those stock-specific targets, you're foregoing an enormous amount of the harvest available on the aggregate. A second way to use these stationary relationships is to come up with some way to vary harvest rate with the aggregate stock. Again, to meet those same stock-specific targets. And there's a variety of ways to do that, and these are just some examples of different methods that have been tested. And a third method that I don't have a graph of is just to use a fixed harvest rate on the whole stock. You find a harvest rate for the weakest stock, and you just apply that to the whole stock complex. Okay, the third way, and the way that I'm really exploring more myself is to use multiple harvest rates to address multiple stock states, and you'd use a complicated computer algorithm in order to calculate what the appropriate harvest rates are at different times through the fishing season. In this case, I use a linear programming algorithm. I'm going to very briefly introduce linear programming. And with that, basically, you maximize some objective function subject to a set of constraints to bound the solution space. And this is just an example of how 4 constraints can block off a portion of your solution space. You would maximize the value of your objective function within that solution space. And why would I use linear programming? There's a bunch of nice things about the combination of linear programming and salmon fisheries. One of the key ones is that the events in the salmon fishery are really sequential. They line up really easily. So converting the salmon fishery into a linear equation is really straightforward. The goals and constraints of the salmon fishery are really easy to define. And there are some real computational advantages to using linear programming. People have been talking about the computational challenges of running a large Bayesian model. A really big linear programming problem still is solved in seconds. So a quick math slide. I want to mention the objective function. The idea is in order to employ a linear program, you need an objective function. In this case, I'm trying to maximize the value of the harvest. So in each portion of the fishery, be it a day of fishing, a week of fishing, a fishing gear, be it gill net or seine, or a fishing area, you allow the linear program to choose the harvest taken in that fishery, and then you calculate the value of the fish caught in that day. And you constrain the solution space by limiting the total exploitation rate. In this case, I'm using a biological constraint. I'm limiting the total exploitation rate felt by any of the substocks in the mixed stock fishery. You transform that into a matrix of constraints, and there's a whole variety of programming algorithms in order to quickly and efficiently maximize the value of your objective function. Well, what does that actually give you? It gives you something really cool. Given a set of stock sizes and run timings, you're handed, for each combination, you're handed an optimum pattern of fisheries opening. So in this graph, the gold bars are the optimum weekly harvest rates in a fishery, and the blue lines are the different substocks running through the fishery. So you can see how the fishing weeks overlap with the different components of the aggregate run. So that's pretty neat. And one of the really nice things about this is, after many simulations and many reruns over the historical data, you see that the pattern of these optimum fisheries openings remains fairly constant over time. So in any particular year, you have a similar pattern of fisheries openings. So that gives us an opportunity to compare the optimum pattern to the existing pattern. On the left is 6 sample opening patterns, and on the right are the exploitation rate curves associated with the actual historical management. And so you can see that there's a gap cut out of the middle of the optimum pattern, and that gap doesn't show up in the historical period. Second outcome is that when you compare an in-season optimization like a linear program to one of these fixed stationary harvest control rules, you get significant improvements in performance. In order to hit an aggregate target or an aggregate harvest rate that meets all the stock-specific concerns, you get less harvest out of the system than if you go in and do an optimization at a finer scale. So this is just a graph of 2 simulated catch histories, one using the in-season optimization and one using a fixed control rule. And then there's a bar graph showing the result of many, many simulations, showing that you have on average, an additional 1 million fish caught, which is a significant improvement in performance. There's some other outcomes that you can get out of this. I mentioned that you see opportunities for improvement in current harvest management by changing the pattern of the openings. One of the neat things about the linear programming algorithm is it will highlight for you the binding constraint. So if there's one particular stock that is always limiting your harvest, you can identify what it is. And then it can be targeted for specific, perhaps enhancement or other management action. And with that, you can also calculate the increase in total value of the harvest given relaxation of those binding constraints, and that will let you value something. If there's one stock that's always binding, it's always limiting your harvest of the aggregate system, you can say, well, if we can improve the productivity of this stock, through a spawning channel or some other program, it would be worth this much money to us. So is it worth investing? And one of the other neat things is this is a particular case where increases in monitoring can actually lead to additional increases in harvest, because when you move from managing on the season scale to the weekly time step, you get this increase in the amount of safe harvest you can take. As you increase your monitoring, you can get finer and finer control, which allows you to shave closer and closer to the margin. So I just want to address some extensions to this. I think this is a pretty neat tool, but when I do a literature search, I've only found a handful of papers where people have applied this. So it doesn't have to necessarily be applied strictly to salmon. It can be applied to any closed time where you have multiple fishing fleets, multiple fishing stocks, or anything like that. One of the other interesting things about it is that the constraints don't have to be biological constraints. There can be, if you can imagine something that's constraining your fishery, you can write an equation to constrain your solution space. A couple of examples of stuff I've played with are looking at catch sharing agreements, looking at, rather than maximizing harvest from the system, maximizing employment, looking at allocation between different fishing fleets. There's a neat study going on Bristol Bay. Curry Cunningham at the University of Washington is looking at how processor capacity limits harvest opportunities. There's only so much fish that can be processed. So how can you optimize your fishing pattern in order to not be catching a bunch of fish that have to sit in your boat waiting to get into a processing plant? And I think I've mentioned this a couple of times now, but these linear programming models are astonishingly fast. So they can be built into your management strategy evaluation without turning it into a 3-week nightmare to run. So yeah, I guess I'm pretty happy with my results, but I'd definitely like to improve my presentation. So if you have some ideas about that, maybe look me up at the poster session. Also, I've got some code and data files on a GitHub site. If anybody wants to take a look at it and give me real detailed feedback, that would be great. And I have an Excel model. Excel has a linear programmer built into it. I have an Excel model I can share with people if you want a more easy to play with version of it. Anyways, thank you very much for your time.